Okay, so yes, today's lecture is on Fourier transform. Okay, I just want to check if everybody's here. Can you hear me? Can you hear me on the channel? Okay. So some people are, they're getting worried that there is too much material. Uh, but actually, it's just whatever we have covered now, and plus the Fourier transform. So, and this Fourier transform is we just we will cover not the whole uh, two lectures, which are lectures 7 and 8. We will cover only lecture number 8 and the problem set. So it is much less material than we had previously. Previously, we had Fourier transform, and then we had Fourier series and Fourier and Laplace transform. So there was a whole lot of material. Um, if you want to sit in the final exam, that's fine. If you don't want to sit in the final exam, then you can talk to Dr. Badar. But in my opinion, it is much easier this semester, and it is a good chance for you to uh, take this course and uh, get over with it. Any questions? You can ask on the live chat. So, Fourier transform. Now, uh, we did the convolution, and the convolution was a method. So, if we have an LTI system and there is an impulse response, the output of the system is h of t convolved with the input, and that is equal to that integral h of t minus tau d tau. Now, here we are doing everything on um, the time domain. In the Fourier analysis, what we do is we transform the time domain to the frequency domain. So I have x of t, and when I apply the Fourier transform, I get the frequency domain. So for every function, there is a time domain and the frequency domain. Time domain is the is the domain in which we usually see the signals, uh, and the frequency domain is the frequency picture of the signal. So the frequency domain tells that what are the frequency components in any signal, and actually both are the same signals, but one in the time and the second is in the frequency. So why do we do the change of uh, um, domain? Why do we need a signal in time domain as well as in frequency domain? The reason is to design a system, and also there are many things which become much simpler in the frequency domain. So for every signal there will be a time domain and there will be a frequency domain. So uh, now if my signal is in frequency domain and I need the output in the frequency domain again, what I do is I also need the h in frequency domain. So once I have x of omega and h of omega in frequency domain, the output is just the multiplication. So this is another advantage of converting a signal to frequency domain, that the uh, the output the to find the output, it becomes much easier. Now, how do we find the frequency domain of a function? Uh, we find the frequency domain of any function by doing what we call the Fourier transformation, or by the operation which is called the Fourier transform. So, what is the Fourier transform? The Fourier transform is uh, so I want to find x of omega, so which is e raised to the power minus. So any function, I have x of t, so I multiply it by minus j omega t and take the integral from minus infinity to plus infinity, and this gives me my Fourier transform. So x of omega is called the Fourier transform. So I have x of t and the Fourier transform of x of t. So to convert x of t to x of omega, I do the Fourier transform. To convert the x of omega back to x of t, I do the inverse Fourier transform, and the inverse is given by this integral. So it will be x of omega e raised to the power plus j omega t d omega minus infinity to plus infinity. So in this way, I can go from the time domain to the frequency domain, and from the frequency domain back to the time domain. All right. So now let us find the Fourier transform of some of the uh, functions. Let us first find, as an example, the Fourier transform of e raised to the power minus at. So example, x of t equal to e raised to the power minus at u of t. And this function is this exponential. Now let us apply the rule. X of omega is equal to minus infinity to plus infinity e raised to the power minus at u of t e raised to the power j omega t dt. And because there is a unit step, the limits will be from 0 to infinity, because before 0 there is nothing. So the limits will change from 0 to infinity, and it will be e raised to the power minus, I can combine the two exponential, omega t dt, and this will be equal to 1 over, or it will be just an exponential, so it is minus a plus j omega t divided by a plus j omega, and the limits are from 0 to infinity. I can write here again the definition of Fourier transform. So this is x of omega here in this case will be, when I put infinity here, it becomes minus infinity. So it will be minus 1 over a plus j omega, and this is e raised to the power minus infinity minus e raised to the power 0, because this is 0. So as we know that e raised to the minus infinity is 1, and sorry, it is 0. So this goes to 0. So this will be, and this is 1. So it will be 1 over a plus j omega. So this is the first Fourier transform we did, and we write it in this way here, that we have e raised to the power minus at u of t in time domain, and in frequency domain it is 1 over a plus j omega. Now the last step is to draw the two domains. So this is in time domain x of t, and in frequency domain it is a complex number, so it has magnitude and phase. Uh, so I can just draw the magnitude, x of omega. So the magnitude of this is x of omega magnitude is 1 over a plus j omega magnitude, and that is equal to 1 over a square plus omega square. So if I draw this in omega, it will be something like this. At omega equal to 0, the magnitude, sorry, there will be a square root here. So at omega equal to 0, it is 1 over a square square root. So this point is 1 over a. All right. So this is the first Fourier transform we did, which is an exponential function. Now, the good news is we don't need to find the Fourier transform in the exam for using the integral. In the exam, we can just, there is a table which I gave it to you. I, I, I sent it to you today. So we can just use that table to find the Fourier transform of the time domain functions. So as an example, I can write some of the Fourier transforms here. And these are given on, if you look at the lecture number 8, which I forwarded to you today. So uh, go to the page number 4. Go to page number 4 and you will see some of these Fourier transforms, which I will write here. So the first one is which we did today, just did. So the first one is e raised to the power minus at u of t and this is 1 over a plus j omega. The second one is the delta function, and the Fourier transform of this is just 1. The third one is the complex exponential, and this complex exponential is, we know that this is equal to cosine omega naught t plus j sine omega naught t, and that is equal to 2 pi delta omega minus omega naught. And the last one here is the rectangular function, and I will draw this all these on the next screen. So this is the Fourier transform of this is the sinc function, which is tau sinc omega tau divided by 2 pi. Now let us on the right side draw all these Fourier transforms. So I am going to, so here I have e raised to the power minus at u of t. The Fourier transform if this is x of t, and x of omega is like this, 1 over a. So this is the magnitude of x of omega. This is the omega axis, this is the time axis. The second function here is delta function. So this is a delta function here at 0. The Fourier transform of this is just 1. So I have 1 all the way at all the frequencies. This is delta of t, and this is 1. Now the next one is cosine and sine. So I have cosine and I have sine, cosine omega naught t and j sine. So this is a complex exponential. The Fourier transform of this is just an impulse at a frequency omega naught. The last one is the rectangular function, which is this function here, uh, t divided by tau. So tau is the width, which means that this is tau by 2 and this is minus tau by 2. And the width of this function is tau. So this is a rectangular function with the width of tau. So the Fourier transform of this function is a sinc function, which is like this. Now, how to draw this sinc function? Uh, the the width of this, the width, it goes to the amplitude. So the amplitude of the sinc is tau at 0. And the first crossing, this crossing, is at uh, 2 pi by tau. So this point here is 2 pi by tau. And this is minus 2 pi by tau. So this is how I draw it. The width goes to the amplitude, and 2 pi by tau goes here. So this is the first 0, and the second 0 is at 4 pi by tau, minus 4 pi by tau. Let me just confirm it here. Is it this one or? Yeah, so this is correct. So now we have done some of the very important Fourier transforms. Uh, Now, what I would like to do is to uh, uh, study some of these properties of Fourier transform, because in the exam, what we will do is we will find the Fourier transform by using the table, which has these values plus some more formulas and plus the properties. So if we combine these two, we can find the Fourier transform of any function. So let us study some of these properties. Let us go to the lecture which I sent you today, and let us look at the first property, which is the property of linearity. This property says that if I have the Fourier transform, so let us do this properties one by one. Um, uh, so let me just delete one side. Let me delete this side, and I will start the first property of the Fourier transform. So the first property is the property of linearity, which uh, so this property is very simple. So if we have a Fourier transform of x of x1, which is x1 of omega, and Fourier transform of x2, which is x2 of omega, then if I just add these two on the time in the time domain and multiply it by any value, so ax1 plus bx2, the Fourier transform will be just a x1 of omega plus bx1 of omega. All right. So this is the property of linearity. So if it means that if we have two functions in time domain and we can add those two functions, so the Fourier transform will be the the addition of the Fourier transforms. So I can, using this property, I can find the Fourier transform of cosine and sine. Uh, as we discussed before, that the Fourier transform of the exponential, complex exponential, is 2 pi delta minus 2 pi omega minus omega naught. This is we did in the last one, this one here, 2 pi delta minus delta naught. So if I have e raised to j omega naught t, the Fourier transform is 2 pi omega minus omega naught, 2 pi delta omega naught, omega minus omega naught. So, and all, we also know that the Fourier, yeah, so we also know that cosine is the sum of two exponentials, plus and minus. So if the Fourier transform of plus is 2 pi omega minus omega naught, then the Fourier transform of minus will be 2 pi omega plus omega naught. And if I add these two, if I multiply by 1 by 2, multiply by 1 by 2, and add them, so it will be j omega naught t plus 1 over 2 e raised to power minus j omega naught t. So on this side, I can just add these two and divide it by 2. So it will be pi, uh, sorry, there is a delta here, delta. So 2 pi delta of omega minus omega naught plus pi delta of omega plus omega naught. And on this side, the sum of the two exponential is cosine. So the Fourier transform of cosine is two delta functions, omega minus omega naught plus pi delta of omega plus omega naught. And so I can just remove this for the time being and draw the cosine here. So cosine, this is my cosine omega naught t, and the Fourier transform of this is just and the amplitude is pi. So pi delta omega minus omega naught. So this is pi delta omega minus omega naught plus pi delta omega plus omega naught. So this is the property of linearity. Now the second property is the property of, and you can also find the Fourier transform of sine using this, as you can see in the next slides. Now let us go to the page, to the slide number 8, the second property, which is the property of time shifting. Now this property is a very important property, and this property says that, so I will just delete these here. I can delete these and I can write the property of time shifting. So time shifting. So if the property says that if the Fourier transform is, if a Fourier transform of any function x of t is x of omega, then if I shift the function in time, so I shift the function in time, I don't need to find the Fourier transform again. What I do is just multiply this by j omega t naught. So this is a very important property. If there is a time shift in the time domain, then in frequency domain, I just multiply by it by an angle. This is a phase. So I just multiply it by a phase of minus j omega t naught. The amplitude remains same. Only the change is in phase. So this is a very important property, and we can find Fourier transform due to of many functions by using this property. As an example, if you look at slide number 9, there is a function of square rectangular function which has uh, uh, this, because now we are in this slide number 9, we are adding uh, two rectangular functions, so I can find the output by using the two properties we just discussed, the linearity and the time shift. So let us do this example, and then we will finish this lecture. And then what I will do is I will record some of the problems uh, as clips. And if you have some other problems, you can also ask me, and I can also record them. And then we can discuss it later on, that how we want to do the final exam. The midterm is okay. The midterm is, we can, because we have already covered the midterm, the problems, it will be just from the convolution in the systems. So the midterm is okay. We can go ahead. For the final, if we need some more time, we can request Dr. Badar, so that we can spend more time on the problems, and then we can go to the for the final exam. All right. So let us do this last problem, and then we can uh, finish the today's lecture. So the problem is, it is on the uh, it's example 3, and it's on page number 9. So I have this uh, this function here, 1 2 3 4, as this function is 1.5 here and 1 here. So as you can see that it is a combination of two rectangular functions. It is a combination of two rectangular functions. Now these two rectangular functions, one of them is this and one of them is this. As you can see, one of them is this function and one of them is this function. And both of this function are centered at 2.5. So this is equal to, this x of t is equal to this rectangular function, which has, I can say that this is uh, zero point 0.5, and I have the second function which is, and this goes from 2 to 3, and the center is 2.5. And the second one is, it goes from 1 to 4, and the center is also again 2.5. Both of them, the center is 2.5, but the amplitude of this is 1. So that here it is 1 and here it is 1 plus zero point 0.5, zero point 0.5. So this is a combination of these two functions. So if I can find the Fourier transform of this and I can find the Fourier transform of this, I can add them to find the Fourier transform of the whole function. So now we just, uh, so we can use the table. We can go to the table and find the Fourier transform of rectangular function. So we know that the Fourier transform of rectangular function, we can look at the table or we can just look at today's lecture. So if this is, uh, if this, the width is tau, the Fourier transform of this is a sinc function like that. So this is rectangular t over tau. The Fourier transform is tau sinc omega tau divided by 2 pi. Now, if I shift this to any other point, I will have to apply the rule of the shifting, which says that if x of t, the Fourier transform is x of omega, then if I time shift, the Fourier transform will be e raised to minus j omega t naught. So I have the same Fourier transform multiplied by the shift, phase shift. So now I have two rectangular functions. I have this rectangular function, which is rectangular. Actually, this is 0.5 rectangular because the amplitude of this is 0.5. So it will be 0.5 rectangular omega, sorry, t divided by 2 pi, t divided by tau. So what is tau? The tau is 1. So it is just 1. And there is a time shift. So it goes from 0 to 2.5. So I can just write the time shift here. So this function is actually zero point 0.5 rectangular t minus 2.5 divided by 1. And this rectangular function, this one is rectangular t minus 2.5, again the same shift, but the width of this is 4 minus 1, 3. So now I have all the information. I can write the Fourier transform of these two and add them. So zero point 0.5 rectangular t minus 2.5 divided by 1. The Fourier transform is this function and multiply by the shift. So this is tau. What is the tau here? It is 1. And it is multiplied by zero point 0.5. So I just have 0.5 here. And sinc omega tau is 1 here. Tau is 1. So omega over 2 pi and multiply by the phase, which is e raised to power minus j omega t naught. T naught is 2.5 here. So multiply by e raised to the power minus j omega 2.5. And the second one is rectangular t minus 2.5 divided by 3. 4 minus 1, 3. So tau is 3 here. And so I will multiply it by 3 sinc omega over omega tau. So omega 3 divided by 2 pi. And the shift is same. So e raised to power minus j omega 2.5. So I can add these two to find the Fourier transform of, because of the whole function. So the answer here is If I add this, it will be x of t, and the Fourier transform will be zero point 0.5 sinc omega over 2 pi e raised to power minus j omega 2.5 plus 3 sinc free omega divided by 2 pi e raised to the power minus j omega e raised to the power minus j omega 2.5. So let us finalize here, and then uh, we can do further talk on the uh, we can do further discussion on the WhatsApp group to see that how many lectures do we need to finish this uh, lecture number 8. All right. Thank you.